All right, guys, we're going to start this workshop. Hopefully, it's not going to be too boring for you. There will be some stuff you will have to do yourself, so you will have to code and actually even make some tests green. So we're going to be a bit more interactive, and the first part actually is going to be like 30-40 minutes, where we're going to explain, introduce a few bits. You've seen already a few presentations maybe mentioning Reactor already, so, and there is another one later specifically about Reactor later on. So we're not going to focus on that part, but maybe more on the hands-on part. Want to start?
Yeah. So we are quickly introduce ourselves. So I'm Sébastien Deleuze. I live in Lyon. I'm a remote worker at Pivotal. I mainly work on Spring Framework 5 and Reactor. Mainly on the upcoming reactive supports, and I'm also a Mixit staff member. Mixit is a conference which is in France.
And I'm Stephane. Well, for the guys who don't know me, and actually we didn't really introduce ourselves this morning with Ross, and I actually work on the project Reactor, currently leading it. And I'm a contributor of Reactive Streams specification. Even if now it's stabilized, we continue having discussions. So we created this specification, and we're going to explain a bit of it in the presentation now. And I commit when I have time to Spring Framework 5, but to be honest, these days it's a bit difficult. A lot of stuff going on around Reactor. So yeah, and I try to survive in London. That's the greatest thing ever these days.
So the first topic is why going reactive. That's more for scalability and stability than for speed, because in fact, when you do reactive programming, you have a small overhead to deal with, I think, binaries and things like that. So that's really more about scalability and predictive capacity planning and things like that, rather than pure speed. The use cases are multiples. A very common one, even if you don't do some big data stuff and if you don't have a lot of users, is a web app that is calling a remote web services. I guess you have all developed such application with a REST controller that itself produces a request to a remote web services that could take 2 or 3 seconds to answer. And with that, with a blocking web framework, with a few, maybe 50 users, you could easily quickly block, because each thread will be blocked, and when the thread pool is full, the web server don't answer. So for such use case with some latency, reactive programming is really interesting. That's also allowed to deal with a lot of slow clients that are usual when you deal with mobile, for example, because you need one thread to serve one client. So if you have a lot of very slow clients, a reactive stack will scale better. Big data, obviously, serve more clients on the same hardware, and event-based development.
Right, so quick reminder, I think you've probably seen that a few times in the conference already, but for anyone who didn't see this kind of slide yet, trying to get through it, what is reactive? So in the past, reactive was used to define actually just event-driven systems, and precisely it was used in UI. For instance, what Microsoft has developed, what we call reactive extension today, was to support UI in the latest development they did. And that notion involved, actually reactive was a kind of slopey notion that didn't have a hard definition until very recently. Everyone was using reactive, the keyword or the buzzword, for a long time, and that actually harmed a bit the design behind, because everyone was thinking like, is it just hype? Do I really need to care about this stuff? And then there was this reactive manifesto, which is nice, but if you like me, I've tried to read it a few times, and I know this stuff. I understand what it said inside the reactive manifesto, but I keep reading it, and I don't understand what's the point about it. So it's actually defining quality of a system, but it doesn't help you understanding how you achieve this kind of thing. It's all good On the theory side, there is the Ahmed law, which is very interesting, showing that the more you, the few times you block, it's actually causing some performance degradation easily in a parallel system. But beside that, it's there. It was the first tentative to get some kind of explanation around reactive, a bit biased by another company, but still available. And then we have the notion of reactive programming, which embraces precisely what you have to do as a developer to really embrace this paradigm. And this is supported nowadays with real definitions, real, real page with what it means, a TCK even. We're going to speak about reactive streams, but real tangible stuff, not like vaporware or this kind of thing. So the reactive programming part is really about changing the way you code. We all used to, do the for loop, all this kind of imperative paradigm, for loop, if, throwing exception, all this stuff, which is replaced completely in the reactive world. You can't throw an exception in reactive world. You can't, you don't do for loops in reactive world as well. We'll see there is a different alternative. So all of that to avoid blocking, and that's really the point about reactive programming. It's about making your code non-blocking and nothing else. And to support reactive programming, we need two kind of things. We need a kind of definition, as I said, because it's a bit sloppy. And we have now, it's called reactive streams. And we will need probably tools that implement this specification or definition. So let's talk first about the definition itself, the specification. So it's called reactive streams. It emerged like 2 years ago with a discussion between us, Pivotal, Netflix, and TypeSafe. And we were discussing about how to really make a real standard that can be implemented at least by Java developers, and really is about behavior, the non-blocking behavior, not really about the interfaces. So it has to be proven, it has to have a TCK, it has to have a clear list of specification rules, all this kind of stuff. And we made our mind, and then Oracle also joined the fun, and that's why now you can find this stuff in Java 9. Unfortunately, not with the same package prefix, because why not? I'm still trying to understand why, but still. This reactive stream specification is available on Java 9, but under a different package name. So we have a bridge in Reactor, and other will have bridge probably to this new Java 9 package for the reactive stream standard. And what reactive streams define is really about sending data from a producer to a subscriber without never ever blocking. And how do you achieve never ever blocking? Well, you have to know if the subscriber can actually do the stuff it has to do without blocking. And how it does that? Well, it simply uses something called a subscription, which is an object you can pass between a publisher and a subscriber, a kind of one-one relationship interface, with one method called request. And this request defines the number of elements as a subscriber you can accept. This is very low-level detail, and what we try to do in Reactor and other implementations, such as ACA-Stream or RxJava 2, is to avoid yourself to do this kind of implementation. So you won't deal directly with the interface publisher-subscriber, but you have to know that the way we communicate ourselves internally between components, that's the specification we use. So what is it all about? In this protocol, actually, we have a few rules, a few important rules. The first rule is we never send more data than actually the demand we've received. And you can see the reverse flow from a subscriber to a publisher. This is really a kind of duplex communication between a publisher and a subscriber, where the subscriber say, OK, I'm going to accept that amount of data. There is a magic number to say I'm going to accept all data, which transform your subscriber into push-only mode, because if you accept all data, you like any kind of framework with a callback, basically. You're ready to accept whatever happens, even if you then forward the data to a blocking remote call, for instance. You don't have limits. So Normally, we use that simply in synchronous world. Sometimes you have synchronous streams, and in that case, it's important to have this magic number, to have that performance of not requesting every time. Otherwise, you have to request, like every 32 items, I'm going to request the next 32 items. And that's the way you are sure that at any time the subscriber will have 32 items, which is good if you do capacity modeling, for instance. Something I used to do as a consultant a few years before. Every time I went to a meeting with a lot of my colleagues, friends, we've been asked, can you do a capacity model for Gemfire? Because I used to consult for Gemfire. Can you do a capacity model for RabbitMQ installation or for this stuff or this stuff? And we were like, yes, we can. Hold on a minute. Yeah, OK, that's going to be requiring 2 gigabytes, 4 gigabytes of memory, and this kind of CPU, blah, blah, blah. But it's actually complete bullshit in some way, because if you don't have a kind of control over the backlog you're ready to accept, how can you say at a given time you're not going to have 10,000 items waiting into a kind of queue somewhere, unless you block, and we don't want to block. So with this kind of mechanism, with the possibility to say, I'm going to request at most 32 items, you can do a real capacity model. Because you know the size of your item, for instance, is the trade book data. You know the average size of this payload. It might be 1 kilobyte, whatever. But you just have to compute in your head a very simple multiplication, which is 32 times 1 kilobyte, and that at most what the capacity of the subscriber is going to be. And that's great, especially, as we said this morning, in mutualized environment, because you want to know in advance at most how many gigabytes this subscriber or this application is going to consume in your cloud-ready environment. That's great for scalability as well, and for availability, because you're not going to go over these 32 items anytime. And if you don't have a limit like that, the physics is going to stop you anyway. If you don't place a limit, basically in the JVM world, we all know what's going to place a limit for you, which is the dreadful out-of-memory exception. So physically, the machine cannot accept at some point a certain amount of data. So that's great. We have a control, and because we have a control over this backlog between many components, we can say, OK, the application is never going to go out of its limit. It's going to be available 100% of the time, because it's never going to pause with the dreadful also JVM pause, the GC pause, and that's great. That's one thing we want to emphasize. More this kind of stability and efficiency than performances. It's not about performances, because doing synchronous call is always going to be more fast or faster than asynchronous code. Asynchronous code needs kind of queuing system. It needs this request stuff to go on every time. So you add overhead into your application. Even if we do that for you, there will be an overhead. We try to be efficient. We'll see that. But still, it mathematically can be faster than synchronous code. That's the way it is. And so we define this contract in a simple jar called Reactive Streams. And if you pull the dependency Reactor Core, for instance, which is used by Spring 5, it's going to automatically pull this jar with 4 interfaces. So we have inside the definition of a publisher, and we keep it simple. Basically, a publisher is something that accepts a subscriber. OK, it subscribes a subscriber. Right. Once he will get a reference of a subscriber, he will call a few methods on the subscriber. And the first one, every time, is going to be unsubscribe, because we need to pass this famous relationship component called subscription to allow the subscriber to request back to a publisher. That's the 1-1 relationship. And so the subscriber will accept first on initialization, once the publisher is actually ready to send data. He will accept this subscription. And once he gets the subscription, the first thing he will do is give me the first 32 items, for instance, or maybe give me an unbounded number of items. And that's quite important, because otherwise you will receive nothing. No request equal no data. Remember the rule. We'll limit ourselves as a publisher to the request we have been receiving before. And if we didn't receive a request, there will be no communication between the publisher and the subscriber. And then there is this set of free methods, very reactive style, because I said it briefly earlier. We don't, for instance, in reactive world, we forget about throwing exception. That's something we don't do. Why we don't do that? Because that would mean that actually the code behind is blocking somehow, and that would be impacting the publisher. That will make the publisher less resilient. If you, as a consumer, subscriber, or even in a service bin, for instance, you throw exception, what happens if you don't catch the exception? You let the exception going back to maybe the server thread, the HTTP thread, and that's totally uncontrolled, and that's something philosophically against what we try to do in Reactive Stream, and it's defined as such. So we have on error, the callback specifically used to receive an error from a producing side. If there is an issue, that's where we're going to interact with the error, and maybe we will resubscribe to a publisher because error is a terminal state, something very important. You cannot receive two errors, and you cannot receive data after an error. If you want to receive data, you want to basically resubscribe to a publisher. Fortunately, a lot of this stuff is done for you or can be done with some operation in Reactor and other implementation, but that's the way it is. The other methods, the onNext eventually is the most important if you want to play with the data. That's where you're going to receive the data. And this method is going to be invoked as many times as you have requested. If you have done a request 32 on subscribe, it's going to be called 32 times eventually. Not immediately, because it's working synchronously or asynchronously. It's very agnostic about the way you compute the data, you transport the data from a publisher to a subscriber. It doesn't have to be on a different thread. It can be on the same thread, but it cannot be more than 32, for instance. And the onComplete is a specific callback you can implement. Well, you have to implement because it's an interface with four methods, so you have to implement everything, something we try also to solve in Reactor. So the complete is here to say if you have finished with the transmission of the data, you can definitely stop and you're never going to receive more data at all. That's a terminal state. So basically, at most you receive an error or a complete or none of them. So you don't have to receive a complete as well. If you're working with Spring Cloud Stream, for instance, it's generally speaking, it's unbounded and unlimited stream of data. It's not really having a completion state because it's always listening, always sending data. It doesn't have to complete. But if you, for instance, work with a publisher which represents a connection, HTTP response, you're going to have at most one data, one onNext, and then you will have an onComplete. That's a limited stream of data. So that's really, to not get into too much of this level of detail, because as I said, this kind of thing is usually implemented by the framework you're going to use, the Reactive Stream implementation you're going to use. But to comprehend the model, you have to know at least a few of these rules. It will help you when you start debugging these kind of implementations. So then we might need, as I said, if you don't want to implement that yourself, we might need a kind of API to wrap, all this overhead and complexity for you. And what means in our world of Reactive Stream an API? Well, it's a set of operations you will apply for one or a few items or even a lot of items. And what kind of transformation you can apply to these things? Well, you can do a kind various or different things like buffering, so aggregating data. And that's very helpful for a use case we also call micro-batching. So we can accumulate data until a given time or a given size is actually reached. And that's a useful operation. Or we can also filter. We can also do the classic, very simple stuff. Basically, we try to map some of the imperative tools you used to have, like a for loop or a if condition, or a throwing exception. We can also, the catch clause is also replaced by a few operations to deal with exceptions. All of this paradigm you know well in imperative world have a translation normally in the Reactive API. And on the JVM, we have a few of the implementation already available. The spec is probably, I said it, it's probably from I'm losing notion of time sometimes. It's from 2 years ago, and we had already working on Reactive Stream spec. Akka Stream had the Akka Stream 1, and already 2. Reactor has a version, Reactor 2 version, which was an initial stab at implementing this stuff. And RxJava didn't have anything, but it has a kind of bridge to translate to Reactive Stream. And we support that as well in Reactor because we work closely with the RxJava team. So that's the kind of implementation you can find to implement this kind of API, where you, instead of using publisher subscriber directly, you can use this high-level API with already available operations. That's the choice you have nowadays. And there is a kind of classification, not done by me, but by my partner in crime, David Carnock, who is the lead of RxJava. He made a classification of reactive libraries, and he called them generations. Basically, they are the more you advance, the more you are in the ladder of the generation. So we are what they call a fourth generation library, because we implement a few things. We are native Reactive Stream first, so every operation are actually implementing Reactive Stream, which is not the case for instance, Akka Stream. Akka Stream implement Reactive Stream at the boundary of the system, but internally the actor stuff, etc., doesn't implement yet Reactive Stream. But on our side, every step of the chain is implementing Reactive Stream. And we have also all the features that qualify us as latest, more recent generation. I invite you to read actually the blog post from David Carnock, because it's better said and written by in complete length. Actually, I recommend the blog from David Carnock in general. It's a kind of Bible for reactive programming in general. This guy is truly a JVM champion, and all these blog posts are very interesting. So, what about Reactor Core? Reactor Core is the version 3 is very recent, because we just released 2 weeks ago the RC1. We're about to release the GA of Reactor Core 3. It's a complete rewrite from 2 and 1. It doesn't look like how it looked like. That's why we used the major version. At first we called it 2.5, but the transformation of the code base was so huge that we didn't want to actually use the half version for that. It was the road to go to a different style of programming, or embracing completely reactive streams, and I think it wouldn't deserve all the work which has been done if we just called it 2.5. So it's 3.0. The good thing about it also is it's natively using and exposing Java 8 Java util function features. So we have an interface with the real world. You can use the operation and you can attach your callback. In general, if you use RxJava, you maybe know something they call action 1, action 2, action 3, etc. Akka Stream is going to use another kind of, I can't remember, another kind of interface to implement to deal with the operation. And also, we chose to use just Java 8 interfaces. So there is, consumer, there is function, this kind of callback, which are going to be placed in your chain of operation. We just reused the Java 8 ones, which is great. Plus all the features, for instance, we can convert to Java 8 stream from and to. We can convert to and from completable feature as well. So really embracing the Java 8 as a foundation, which means you need Java 8 to have Reactor working on your class path. And the ecosystem, I briefly mentioned it, but the ecosystem is one of the greatest things we had the chance to do with this version is to really collaborate between different sensibilities and different team of people, actually, to create what we find the best compromise for all use cases. So the biggest part is actually, of course, the Spring team, because I myself in the Spring engineering team, and we had to support this Spring 5 story about reactive. So the collaboration was super close, which is great, because the feedback we got from real use cases and real world ardent API developers we have in the Spring team helped to develop a quite nice and comprehensive set of API for reactive streams. On the other side, another sphere of influence is reactive extension. And precisely, the lead of RxJava is actually contributing nearly half of the code of Reactor, which is interesting as well. But we have a kind of deal where in Reactor Core actually is allowed to develop any kind of crazy ideas we're not married to reactive extension, even if a lot of operations look like reactive extension. If you know them, you know you can, and they're well documented actually. If you go to the Reactive.io, ReactiveX.io site, you will see a lot of documentation. It's really used, especially in the Android world. Actually, 70% of RxJava users are from the Android world, not necessarily from the server side. And this knowledge, this reactive extension knowledge and concurrency knowledge from David Carnock, the lead of RxJava, really benefited us. And we went further. We have even optimization that doesn't even exist in other implementation, what we call, for instance, operation fusion. So if we detect a few things, we can optimize without you to worry about. Even if you start writing a lot of verbose Reactor code, we're going under the hood to try to optimize the stack. Because we're really about performances as well. That's something we inherited since Reactor 1. I'm really keen on microbenching actually. And we have this Flux, which is the ReactiveX translation of reactive streams. We have a few operations inside. It's something that is the mirror of Java util stream, but also work with the latency, the subscription part where you request. So we have a lot of operations in Flux that deal with many elements, including micro-batching ones like windowing or buffering. And we have Mono, which is like the reactive side of the completion stage. So you can actually, the difference between that and the completion stage is actually about the push-pull mechanism, and we're going to actually emphasize on that just after. But that's a reactive version of the completion stage, basically. And we try to work on other things that have not been done yet for reactive streams. It's work in progress, and especially now we have more clear room to work on this kind of extra support for debugging or visualizing reactive streams. We work on the console, for instance, to deal with, because it looks like a stream in the end, a graph, sorry, of operation. When you have multiple operations, you can actually show them on a kind of graph, etc. We're not there quite yet because it took a lot of effort to actually get this Reactor Core 3.0 out. But that's, that's a work in progress, but that's actually coming from a real version of stuff that is working, but we're not exposing much more until we have a solid version of that. But bear in mind, debugging and tooling is going to be a strong story for us, because otherwise we're not going to help anyone getting into that world. It's already hard enough to get into reactive world, so if we want to really provide all the help we can and all the experience we can around this stuff.
So, unlike Stéphane, I'm not a native reactive guy. I mean, I had to learn all these things. And when I started to work on that for the Spring Framework project, I was interested about comparing the various asynchronous types, because we already have some types in Java. And I have tried to classify that like that. So we have no value, single value, and multiple values. So in regular blocking world, no value is void as a return value. For a single value, that's t. That could be an object, any kind of object, or a future of t. And for multiple, I put future here because to get the result of a future, you have to write future.get, and this operation is blocking. That's why I put that in the
if you see
row. Future
something and at the same time the same blog post reactive, you know that someone is actually lying to you or screwing with you. Yeah. So that's not really true. Every time you block, you're blocking. There is no blocking or off blocking.
That's asynchronous but blocking. So that's future is really. I don't know any good use case for that yet, but maybe I will find that. Multiple values. We have iterable, collection, stream. Stream is not really designed for dealing with latency. That's really said by the guys from Oracle. That's why we really need Flux and observable and things like that. Stream is not designed to deal with operations that take time, like everything that implies a network. So that's why we need other types. For non-blocking, we have the completable future, which implement completion stage. So if we want to represent a no value, we write completable future of void. If we want to represent a single value, completable future of t, and if we want multiple values, completable future of list of t. But that's non-blocking, but you have to wait that every element of the list has been received to get the result, so that's not really a stream, that's an asynchronous collection. Reactive streams, we have seen that we have a single main type, which is publisher, so publisher of void, publisher of t, and publisher of t. So you may ask why don't you use publisher everywhere, since that's a standard. Mm-hmm. But there is multiple reasons. You can't do really anything with a raw publisher. You have not operation. But also, when you are writing your repository or your service classes, if you return publisher of t, you have no idea if it returns one or multiple elements. That's a little bit like in the first version of RxJava, where there was only observable and no single types. And when you write your service layer, we are in the Java world. We like to have static typing, and we want to provide some semantics to explain that we will return one or multiple values. So that's another reason to use types like Flux and Mono to differentiate that. RxJava has a special type for no value that's completable, single value that's single, and multiple value that's observable. And in Reactor, we have mono of void for no value, mono of t, and flux of t. If you want more details about how these types compare, you could have a look to the blog post I wrote, Understanding Reactive Types, that try to summarize that. And yeah. So Reactive Spring, we have talked about that in previous session, but Spring projects are going reactive. That means they are also support reactive programming. We are not stopping other regular effort. Reactor Core is a reactive foundation. We provide some RxJava adapters. And in Spring Web Reactive, you will be able to choose your web engine. That means we do not only switch to a reactive core, we also try to improve what we can, because we don't create a new web framework every year. So we try to make our best to do that. And the idea here is to avoid the hard dependency on servlets. So we support servlet 3.1, but that's a web engine, and you could use instead Undertow or Oneti. We don't have hard dependency everywhere in Spring Web Reactive, unlike in Spring MVC, where the servlet API is used everywhere. So servlet is really used as an engine, and you have the choice of the engine you are going to use. So the Spring Reactive experiment has now been merged in Spring Framework and has been released as a Spring Framework 5 M1. And there is a Spring Reactive playground in my GitHub that contains a sample application with regular web services, server-sent events, things like that. So if you want to go there, it's github.com/sdeleuze/Spring Reactive Playground. So here is an example of a regular blocking controller implemented with Spring MVC. So we have a user controller, a safe capitalized method. We take a request body list parameter, and we uppercase every name that we receive, and we save that in the repository. The blocking repository interface is a regular, like the Spring Data ones, and that's all. If we want to have a look to a controller with reactive types, you see that instead returning a void, we are returning mono of void. That's in order to be able to communicate to Spring Web Reactive that the request processing has been finished. Because a big difference is that in previous version, in the blocking one, the method will return when the processing is finished. Here, we are just defining what kind of operation we will apply when we will receive some data. So basically, this method returns directly, very quickly, That's non-blocking. And this method allows us to basically define the processing chain that we are going to apply when some data will be received in the flux of users. And we use the map operation to uppercase the name. If you have a look to the Reactive repository, you see that we return a mono of void or flux of t instead of some collection or void. And you will see that as input parameter, we still use publisher. Generally, in our API, we try to keep using publisher as an input parameter because basically that allows us to accept any kind of publisher. I mean, when RxJava 2 will be out, it will support directly a publisher. You can use any kind of Reactive Stream-based API type, I mean. But for return values, as I said previously, we want to be able to do something with the return value, to use some operators. We want to communicate the semantics 1 versus n. So generally, in our guidelines, we use a raw publisher as input parameter and Reactor implementation mono of Flux as a return value. So this graph tries to show the differences in terms of memory consumption. In the blocking example, basically, we are going to buffer all the users that we received. And when we have received everything, we deserialize that with Jackson. And we serialize the capitalized version. But we have to wait to receive every user. So imagine that you have 100 users, for example. You are going to put all these users in memory, pass that to Jackson in one step. It will deserialize the thing and the other way around. So yeah, that's not really a streaming behavior. With the reactive implementation, what we are going to do, so we received a list, an array of JSON of users. And we are going to deserialize each individual users that we receive. So what we are doing, because Jackson is still blocking, we have not yet a non-blocking reactive version of Jackson. What we do is that we analyze the JSON array, and we identify each individual users in that. And as soon as we receive the user, we deserialize that with Jackson. And the processing, the capitalize, and the save in the database can occur. So we don't have to wait to receive all the users before starting processing that. We can start that before and consume less memory.
Just one quick point. It looks amazing like that you have such an improvement, but the terrible truth is it's going to actually consume maybe more of your CPU, so, or even be slower than the usual blocking approach. Yeah. So keep that in mind, because we don't want to over-advertise the reactive story neither. You have to remember it's a story of trade-off. Okay, you have a control over your memory and your backlog, but that doesn't come for free. And if we wanted to show like the bad diagram of the difference between the processing latency of one and another one, of blocking and reactive, we will be losing to this side and would be not that nice. Just to keep that in mind and to not over-advertise the side, this side effect. Yeah,
that's important, and that's why we try to use the type that you are using in the request body or response body in your controller as a hint about how to serialize and deserialize the data. I mean that if you are using Flux, for example, we are using the streaming behavior, so we will consume more CPU, but we will use the streaming behavior and serializing and deserializing in individual users. But if you use a list, for example, we are going to use the Spring MVC regular behavior to deserialize or serialize the full list without processing individual elements. So we use the type that that you are using in your controller as a hint about how processing that. Even if internally everything is Flux and publisher, if you use a type list, that means for us that you want a regular processing one time the full collection. If you use Flux, that's a hint for us in Spring Web Reactive to say, okay, that's a streaming behavior, so process each individual element in a streaming way. That's another diagram that shows that, yeah, if the database is MongoDB, for example, the users will be saved in the database as soon as they are received, rather than having to wait all the users have been received. So you could have also a controller with reactive return values. So here we have a find all method that uses the reactive repository that allow to optimize the serialization when using Flux instead of lists. So you can begin to serialize the data before with drawback that Stephane talked about. And that's also a very good use case for server-sent events. So in the Spring Framework 5 M1, we support server-sent events. If you have used server-sent events with Spring 4, we have a SSE emitter type that is really designed for that. But here, we just have to use a flux of user of a flux of server-sent events, which is a new type that we are providing with Spring 5. Because that's just a perfect match for the server-sent events behavior. That's an infinite stream that will push elements to the client. So if you return a flux of users, for example, as soon as we receive a user, we serialize that with Jackson, and we push that to the client that will receive the stream. So this kind of use case is really stream-oriented and is a perfect use case for types like Flux or
just a quick precision. It seems like that you will be able to return to pass in the Flux as many users as you want, but behind, remember I talked about back pressure, so there might be some story about back pressure somewhere. You don't see it actually here. What we have, in fact, is in the Servlet 3.1 bridge or Netty bridge we use, we're going to actually see the buffer, the backlog we currently have. So for instance, Netty will have 128 elements in its backlog, and at this stage, it won't ask for more data. So it won't try to write back the response, the server-side event to the client, which is great. Otherwise, you'll be pushing in only in an unlimited, unbounded fashion the data, but there will be requests actually, and you could even monitor that. There is an operator called log, and you will see like a coming flow of requests, 128, 128. It's not going to be unbounded requests. It's going to be as soon as Netty has the room to write back the response, it's going to request you, not before. And that's the way we every time become non-blocking. Otherwise, if you didn't have such limit, you will be trying to push back to push to the backlog of Netty all the user you want to send, and at some point, you know, the backlog has some limit, especially in Netty, you will be blocked. So that's the way we work. Usually, when we have a queue in the middle of our operation chain, we will request at most the size of the queue, and we will try to maintain this queue replenished by, for instance, starting with a request of 128 if it's a size of 128, and then after 64 elements, we're going to ask already for the next 64, which is also called prefetch. So we're going to try to maintain the queue size as much as we can, but we're never going to go over that to go overflow.
So we have also a reactive HTTP client. Really, in Spring Framework 5, we have a big focus on the HTTP client that will be provided in addition to the REST template. And also, we don't just support reactive types. We also try to provide a new Fluent API, extensible API that will be, we hope, more flexible than the current REST template. So that's a really important point, especially for cloud use cases where, especially with HTTP2, a use case where you have a reactive server and a reactive client that discuss server to server. That will be a use case very, very common. So we have a big focus on the HTTP client on Spring Framework 5. So this reactive HTTP client get a mono. So that's like if you get a compatible future of person. So we have a Fluent API that allows us to specify the URL to request, the headers, the media type, etc. And we extract the response as a single result. The API may change. That's not final. If we want to get a Flux, you said previously, I wrote extract body person class. Here we are extracting with the body stream extractor, and that means that I will receive a Flux. So This is intended to parse some JSON array, for example. And that's quite flexible. That works for regular JSON arrays. So if you have a regular REST web services, that could be non-reactive, we just parse the JSON array and we put the result in the flux of person. That also works with JSON streaming. So if you are requesting some API like Twitter API, when we receive some JSON objects that are eventually separated by some separators or not, we identify that. And that also works, that will work in the Spring Framework 5M2 for server-sent events, because we will provide a server-sent events client that will dynamically parse input data. Flux is a perfect use case, again, for that kind of streaming behavior. And I said previously, that's a perfect fit for microservices, especially when we will have the HTTP2 support that will be coming. So we have spoken a lot, so now that's your turn. If you have a computer, the idea is to go to the code. We have some exercise for you. Hopefully, we won't be really useful, but if you need some help, don't hesitate. So the idea is to go to github.com reactor/lite RxAPI hands-on. So yeah.
Yep.
The repositories that you have shown of they all identifying tasks. What if you have a procedural query?
Interesting question. So the question was, if we have Spring Data support for reactive streams, what is it about the pageable support? Actually, it fits quite well, and I know the Spring Data team is working on the paging support for reactive stream, because we can actually translate a request of 32 items into a select from limit, with a maximum. I'm not sure where this story is right now. I think there are a few explanations already if you look at the slide from Mark Polish and Christopher as well. Actually, I think maybe there is actually Christopher around, or it's not around, too bad. But the idea will be to page as the request comes in, basically. So that's great, because, again, the idea of reactive streams is to leave the data where it is until you're ready to consume it, which is great. So that's quite efficient, and that would be the case for pagination. Sorry if I don't get exactly the answer, but you should have a look at the Spring Data presentation in case they explained it.
What happens when you're doing the web client? The web client is have a pageable microservice.
Mm-hmm.
So we have to basically build that request in that one so that
That's a great question to maybe ask the guy hiding here, because there is a bunch of guys around who implemented all of this stuff for the Cloud Foundry Java client, and they consumed the Cloud Foundry REST API, which has some, pagination support as well. And they do have some great experience to share about how you translate REST API into a pagination. But you can have a look directly at the source code, because the Java Cloud Foundry client is available on GitHub. But ping the guy here. Can you raise your hand, man? Yeah. After you can ping him. He would be happy to explain that to you.
Okay. So for the exercise, the idea is to clone this GitHub repository. So you will get that. So that's a Maven project that you import in Java 8 IDE, like IntelliJ IDE or Eclipse or whatever. And you will see that you will have a few classes with part 1, part 2, etc. So the idea is to begin by the first one. And if you have a look to the source code, you will see that each time there is a test that is already written by us. And you have a to-do. And the idea is to change the return null here by something that will make the test green. Okay?
Bear in mind, it's often going to be a 1 or 2 liner, so don't overthink it.
That's very short. So here we say to do return an empty flux. So the idea is to make you search in the documentation. So
The Java documentation.
Java documentation, because the reference documentation is not written yet. We are working on that. So you have the free links that are really useful here to the Java doc. So test subscriber, you are not using that a lot. That's a test that we have written that are using that. But that's basically a way to test what is in a Flux or a Mono. So you see in the example.
That's quite great because you can do assertion about the sequence of elements you receive. And it's hard to kind of test asynchronous code in general. And this kind of thing is the helper you need to test reactive streams.
Yeah. So here you see we have test subscriber.subscribe, which is a static method that allows to subscribe to a publisher. And here we put await. That means that we are waiting the complete signal, and after that we assert values. So
only in testing, await. Only in testing.
Yeah. So you see there is various assertion, assert error, assert. Yeah, there is a lot of things that allow to test your Flux and your Mono. And you have the Java doc. The main place where you will have to have a look is the Java doc of Mono and Flux. So. To make that more easy, when you have to create a Mono instance or a Flux instance, usually it's in the static methods. For example, you have mono.create, mono.empty, mono.fromCallable, etc., etc. So you have various ways to create a Mono or a Flux based on such static methods. You have the same if we have a look in Flux. And we are going to the static methods. There is other ones, but yeah, flux.empty, flux.error, etc. And when you have your Flux or Mono created, you can go to the instance method and you will find a lot of operators. And the idea is to find the right one. So. The idea is to search in the documentation. Don't be afraid. The idea is to make you learn that API. So there is a complete branch. So in master, you have all the to-do, and you have to fill that. And if you don't find the solution, don't panic. You can go to the complete.
But you won't do that. You need to do the exercise before. Of course.
That's to allow you to finish the exercise when you will be at home. And if you are really blocked at some point, you could just have a look quickly. And the idea is to make you learn the API. So yeah, you have the solution here. You
need to feel like what it is about to actually write non-blocking code versus blocking code. That's really the deal. Because the learning curve for this kind of thing is quite hard. So once you get on it and you've understood the first concept, it's really easy then to go on, and even to understand all the frameworks such as RxJava or Stream, because they implement the same kind of paradigm. But the mindset shift is really what we try to get you familiar with.
So we start really simple. So the first exercise, part 1, is to create some Flux instance. Okay, so with the static methods. The part 2 is to create Mono instance. So Flux is for multiple values and Mono is for single values. The part 3 is to allow you to learn how to transform the data. For example, we have seen previously an example about how to capitalize the data. So that's an example. You have synchronous and asynchronous transformation. So you will learn both type. Part 4 is about merging. You have 2 Flux, for example, and you want to merge the result. Part 5 is more about understanding reactive streams with managing the request. We have seen that in reactive streams, if you don't ask some data, you will receive nothing. About this part, I would like to explain you just something really quickly. If you have a look to the test subscriber, okay. The test subscriber is what I have written in the exercise. And when you do test subscriber.subscribe with a publisher, by default, if you read the documentation, create a new test subscriber that requests an unbounded number of elements. That means that when you do test subscriber.subscribe, by default, it requests long max. So basically, it requests a maximum of data. We have done that because the usual error was to you do test subscriber.subscribe and nothing is requested, and yeah, basically nothing happens. If you want to control yourself how much data is needed, you are using the second version, which is test subscriber.subscribe that takes the same publisher, and you specify with n the initial number of elements that you want to request. So if you want to subscribe with test subscriber without requesting some data, you are using to write test subscriber.subscribe, my publisher, comma 0. And after that, you will directly do with the subscriber.request 1, request 2, request 10. You will manage yourself the demand. So the part 5 is really about that. The part 6 is about other operation. The part 7 is about passing from the reactive types to blocking ones. The part 8 is about converting RxJava to reactor types, and the other way around. And the last part is how could I use some blocking API in a reactive pipeline. If you don't have the time to finish, that's not an issue. You have everything to finish that at home if you want. And if you need some help.
You can even just go now and catch up with the other session and do that tonight yeah. with a drink and in face of a machine or casino, something like that. But also if you have questions right now.
Yeah, if you have other questions about the presentation or nothing directly related to the exercise, don't hesitate.
Later, after the session just after, which is really about Reactor 3 updates and all a bit more coverage about the stuff we do and under the cover, and even more like Reactor Core.NET and Reactor Core JavaScript, because that's also two things interesting we are working on. That's, if you're interested, you can come by after. Otherwise, if you have any question, yes? Yeah. Right. What you're going to see is probably slightly less API because it's a bit more focused and we don't try to implement everything in Reactive extension. You're going to be familiar with the paradigm because it's actually the same. And bear in mind, a lot of this code is developed by the RxJava lead as well. So it's not only me, for instance, it's also the lead of RxJava. So it's just a kind of improvement on many things like efficiency, like the fact that it implements natively Reactive Stream, which changes a few things and a few behavior. Because RxJava and Rx in general was really designed for push-based applications. And in fact, the problem they have with RxJava 2 is they had to come out with a new type, so you know about observable, you know about single and completable maybe. And in RxJava 2 you will have a new one which is called flowable, which is actually doing the same thing than Flux. So they didn't want to break some behavior because something changed in terms of back pressure and in terms of how we manage a state as well. I think it's just a story of maturity, basically. We iterated a lot. We did a lot of mistakes, including in Reactor 2. And in Reactor 3 or RxJava 2, we just tried to fix these mistakes, basically. And that's where we are. And compared to ourselves to RxJava 2, for instance, Reactor 3 versus RxJava 2, it's about the API, the complete API, the implement. And I said they have 4 types. We only have 2. That's a bit different, and they are tied to their Reactive extension, so they want to implement all the concepts. For instance, you can have a hint at the maybe the coverage of the API because of the size of the jar. RxJava 2 is also about 1.500 megabytes, and we are more like 900 kilobytes. So you see, we have less stuff. But we find with that because we don't try to over-implement all reactive extension, and we have a mission to also do a easier learning curve from the people coming from non-reactive world. They don't want to be overwhelmed by 10,000 methods. They want to understand and have a few API to comprehend. And the last thing is RxJava, and including RxJava 2, is unfortunately still stuck to Java 6 compatibility support. So they have callback, they have implemented themselves, action 0, action 1, etc. We use Java util function. And they suffer from some efficiency issues because they don't have access to the latest, greatest stuff in Java 8. But the trade-off is, and that's why they do that, Android works for them. And as I said, 70% of the RxJava use base is actually from Android world. It's not the server-side guys, actually. Even if you can use it, it's Java stuff. So that's a few differences. We have probably a more emphasis on performances, probably, and efficiency, and focus on that. And that's it. Nice.
One additional note, you can use Reactor 3 on Android, but only on Android Nougat for the moment. So
yeah.
That will be.
If you're really motivated to use Reactor in Android environment, you can, but you probably need the latest shiny one.
Yeah, it may be possible to run it on other version with Retro Lambda and things like that, but we have not tried yet. So that's possible, but that's a trade-off. And for server side, I mean, we have a very focused, very lightweight library, Java 8 based, and since Reactor 3 is designed to work also with Spring 5, which is Java 8 based, that makes sense to have the same requirements. So. Excuse me? Yeah.
Yeah, go work, Sebastien. I watch you.